look at it this way, Charlie. At least we're not stuck anymore.
I've just got to get a new partner.
Vectors are very useful when we want to predict how an object is affected by forces. As we saw, considerable energy can be wasted pushing a car out of the snow if force is applied in the wrong direction. But there are other ways to move a car. Instead of pushing, we might attach a rope and pull it. Two pullers on the same rope, though, could get in each other's way. And to get better traction, they move off to the side where it's easier to pull. But are they using their energy efficiently? Let's find out. The angle the ropes make at the car is 60 degrees. Pete pulls with a force of 450 newtons, Jim with a force of 600 newtons. Armed with this information, we can work out how a single rope pull in front of the car compares to the double rope pull at the sides of the road. Simplifying the diagram, we can represent the two pulls as vectors. Next, we'll move this vector to the terminal point of the other and draw the resultant. By rotating the vector diagram until the 600 Newton vector is horizontal, we're able to resolve the 450 Newton vector into its horizontal and vertical components, and find the ordered pair for the vector. The ordered pair for the horizontal vector is easier. It's simply 600, 0. Now, by adding, we get the ordered pair for the resultant. And the magnitude of the resultant can be found, as usual, with the Pythagorean theorem. Angle theta is calculated using the tangent ratio, 25.3 degrees. Because Jim and Pete decided to use separate ropes, they were only able to exert 913 newtons of forward force. However, if they'd used the single rope to pull, they could have exerted a total force of 1,050 newtons. So we've found the answer to our question, and as it happens, they didn't use their energy as efficiently as they might have, and the car remains stuck. Jim heads off to get help. This is a wheelbarrow with a heavy load of sand. By lifting vertically, Jim raises the load, but lifting alone has not moved the wheelbarrow forward. He must angle a lift force forward to provide a horizontal push component, even though this will reduce the vertical lift. If the vertical lift needed to overcome the force of gravity is 500 newtons, and it's angled forward to 55 degrees from the horizontal to start the wheelbarrow rolling, he gains a forward force of 500 cosine 55 degrees, or 287 newtons. But his vertical lift is reduced to 500 sine 55 degrees, or 410 newtons. Now, however, the force of gravity is greater than the lift force. Therefore, Jim must increase his force enough to bring the lift component back up to 500 newtons. This requires a force of 610 newtons. If Jim were in a hurry, he might change the angle of push to 14 degrees. But a few calculations will show that the force required would be somewhat beyond his ability. More than 2,000 newtons. Force vectors are everywhere. Builders need to be concerned with snow loads on the roofs of houses. We don't want forces taking over and ruining a perfectly good structure. The force of gravity pulls the snow straight down. This vector can be resolved into two components: the perpendicular component, which represents the load on the roof beams, and the parallel component, which represents the tendency for the load to slide off the roof. Keeping the snow from sliding off is the force of friction on the roof. If the roof has a low slope, the friction force counteracts the parallel component of gravity, and most of the load must be supported by the roof beams. When the slope is increased, however, the parallel component becomes greater, and the snow slides when the force of friction is overcome. The sloping roof is an application of an inclined plane. A mass on an inclined plane is pulled vertically downward by the force of gravity. The force of gravity has two components. One is perpendicular to the surface of the plane and can be thought of as the push of the mass against the plane. The other is a component parallel to the plane, tending to cause the mass to slide. This component is opposed by the force of friction, just as the perpendicular component is opposed by the reaction force of the surface. Until it starts to slip, the mass is in equilibrium with each of the forces perfectly balanced. If we add the friction and reaction forces, we get a resultant which is equal and opposite to the original gravity vector. Let's look at a practical example. Gravity is pulling a mass downward with a force of 500 newtons on an inclined plane that is angled 20 degrees to the horizontal. The gravity vector can be resolved into its two components. Our knowledge of similar triangles tells us that angle theta also equals 20 degrees. The perpendicular force pushing into the plane's surface is 500 cosine 20 degrees, or 470 newtons. The parallel or sliding force is 500 sine 20 degrees, or 171 newtons. The sliding force is balanced by the force of friction, and the perpendicular force is balanced by the reaction force of the plane's surface. As with the snow on the roof, the forces will change as the slope changes, and at some point, the load will slide.
What was that?
Relax, Ed. You're full of tension these days. What's wrong?
Oh, nothing, Charlie. I'm just really excited about everything you taught me about vectors. I know all about magnitude and direction, velocities and forces. You showed me the inclined plane. And best of all, I even learned how to swim.